Okay, we're going to be studying a topic called work and kinetic energy. And right away, what I want you to do is get rid of your current understanding of work in terms of like I'm doing homework or I need to get a job, which is my work. We're going to define work to be something different in physics. But first of all, let's talk about kinetic energy. So what is kinetic energy? I think you've probably heard of the word kinetic before. Kinetic talks about motion. So kinetic energy is the energy associated with motion. And kinetic energy is, which we'll call Ke, equals 1/2 mass times velocity squared. So the kinetic energy is the energy associated with motion. So that's why we've got this velocity component. But also we know that as something's moving, the more mass that it has moving at some given speed, the more energy it would have. So what are the units of this? Well, the units would be the units of m, which are kg, times the units of velocity squared, so meters per second squared, which simplifies to kg times meters squared over second squared. It's kind of a bit of a mouthful, kg times meters squared per second squared, and it's so important that it's given its own special unit, which is called a joule, which is a measurement of energy, where 1 joule, 1 J, equals 1 kilogram meter squared per second squared. Okay, but let's investigate this idea of kinetic energy a little bit further. So if we think about how do you change kinetic energy? So let's start with this equation that we've seen a bunch before from constant acceleration motion. And let's imagine that we take this equation and we multiplied everything by half mass. So you'd get 1/2 mass times v final squared equals 1/2 mass times v initial squared plus 1/2 times 2 acceleration d. Oh, 1/2 mass times 2 acceleration d. Well, what does this simplify to? Well, we just looked at this term. That is my kinetic energy, and I'll put a little subscript f to be like final kinetic energy, equals equals this, which is my initial kinetic energy, so Ke naught, my initial kinetic energy. And then if I simplify, the 1/2 and the 2 go away, and what I'm left with is MAD. Mad. Well, this part of this should, we could simplify this a little bit more, and part of this should jump out a little bit. Whenever you see MA in physics, well, what is that? That's our force. So we could rewrite this now as our kinetic energy final minus our kinetic energy initial equals, I can rewrite MA as just force times D. So resaid, we get that the change in kinetic energy, final minus initial, equals force times distance. So what we just investigated or recognized is that in order to have a change in kinetic energy, what we need to do is apply a force over a given distance. So when you apply a force over a distance, it will supply, or it will create a change in kinetic energy. Well, what is this force times distance? It is work. We define it as work. Work is this measurement of force times distance. Well, what are the units of work? If we look at just force times distance, it's Newton meters. But if we expand Newton meters, Newtons is just kg meters per second squared times meters, or kg meters squared over seconds, which is exactly the same unit as we had before, which is joules. Work is measured in joules. So, and this should come as no surprise, because what we just looked at is that the change in kinetic energy equals force times distance, and kinetic energy is measured in joules, and force times distance, which we're now defining as work, is also measured in joules. Both sides of the equation should have the same measurement. Okay, but if we think about what's going on, so now let's think about a force being applied at an angle, theta. If we think about just the force here that's doing work on the block, and so that's the language, the force is doing work on the block. If we were to break this into its components, F in the x direction and F in the y direction, which is the only force that's causing it to move? And you could make an argument that Fy definitely influences the motion depending on friction. But in terms of the value of the F component that's providing the motion, this is it. The F in the x direction is what's going to cause it to move along the x direction. So when we talk about work equaling force times distance, what we're talking about is force in the direction of distance. And if we want force in the direction of distance, so force that's in the direction of, let's call it, instead of distance, displacement, multiplied by displacement, that's what work is. Work is doing force that's in the direction of the displacement multiplied by the displacement. That is dot product, and that's why we were studying dot products a while ago. And just as a reminder, what that dot product equals is F cos theta times d. That's the magnitude of it. And remember that work is a scalar, so the magnitude of work is the same as the scalar of work. So just to kind of illuminate this with a picture, what we're saying is that when we're talking about work, we are looking at the force that's in the direction of the displacement. Let's look at an example of that. Let's say I have this block. It is being pulled up with a force of 10 newtons, and it's at an angle of 20 degrees. And we're going to displace it 0.5 meters. How much work is done on it? Well, the work done on it equals F dot D. And using one of our equations for work, we get that that would be 10 cos 20 times 0.5. Using the vector calculations for work, what we could have done is we could have separated this into unit vectors. So force would have been 10 cos 20I plus 10 sine 20j. And our displacement would be 0.5I. And so when we multiply those, all we're doing is we're multiplying the i's by the j's. And in this case, our displacement had 0 j's. and you get the same value. And when you do that work, what is the result of that work? Well, the result of that work is going to be a change in the kinetic energy of the block. It's going to result in it having a new velocity. And so we have this important theorem, which I've already sort of said, which is that it's called the work kinetic energy theorem, which says that the work done equals the change in kinetic energy of a system. Or we could write this as FD equals kinetic energy final minus kinetic energy initial. And this is provided, and we should do F dot D. And written this way, this is provided that F is constant. And we will we'll look at how to address it if it's not constant in a second. This is a very important theorem which we will be utilizing quite a bit. It's very powerful in terms of doing mechanics in physics. So let's think about this problem here. We've got a box that's being moved in that direction, and there is a force being applied down on the box at an angle. So there's this force here. And we know that D equals -3 meters I, and the force equals 2 newtons I plus -6 newtons J. It says if the mass of the crate is 4 kilograms and the initial velocity is 10 meters per second, find the final velocity. Well, the way that we can do this is we can say, well, the work that's being done on this object is F dot D, and the result, and that equals -6, the units being joules, and the result of that work is a change in velocity. So we know that that work, -6J, equals kinetic energy final minus kinetic energy initial. Well, kinetic energy, we know, is just 1/2 mv squared. So we get -6 equals 1/2. Our mass is 4. Our final velocity we don't know, so final velocity squared minus 1/2 mass times my initial velocity, 10 squared. And then I can solve this to find final velocity. So this is another way in which we can find velocities other than the methods that we learned in the first part of the year. So we get -6 plus, well, that value, 200, equals 2 times final velocity squared. So our final velocity then would equal 194 over 2 square rooted meters per second. So by investigating the work done, the force over some distance, F dot D, we'll be able to use and find the final velocity. And then the last thing, or two more things, work done by gravity and a variable force. So this is a classic idea, which is you've got some book, and we're going to take this book and we're going to lift it up and put it on a table. So the book, just again, the book was on the ground, we lift it up and we put it on a table. How much work did you do? Well, if we think about, here's our initial situation and here's our final situation. Initially, the velocity initial equaled 0. And then when we put it on the table, the final velocity equaled 0. So the change in the kinetic energy must equal 0. So the net work done must equal 0. Well, what was doing work? There was the work done by me, and there was work done by gravity. And this, as I said, must be 0 because the change in kinetic energy was 0. So, well, the work done by me then must equal negative the work done by gravity. Now, it's kind of funny to think about gravity doing work. It's not like gravity is a person, but the work that is done by the force of gravity. And when you say it like that, the work that is done by the force of gravity, well, we know that the force of gravity on this thing is just mg. So the work done by me equals F dot D, where F is the force of gravity, which is negative mg times D, which is the height of the table. And remember, that whole thing was negative. Therefore, the work done by me, and in order to find the work that I did on this, I had to investigate the work that gravity did on this. So the work done by me is mgh. Last idea here is, what if we have a variable force? What if our force is not constant? So let's just say that, I have some force, and let's just have it all in the x direction, some force in the x direction that equals, let's say it equals sine x plus 1. And I want to know the work required to move block 1 meter. Well, if we draw a picture of what's going on, if we have x and force, we realize that our force depends on our x position. And if I draw in my graph, if we think about a little sliver of this, where that's dx, and this value is f, the area of that, little bit of area, equals f dx, and f times a little bit of x is work. Which then lets us see that a better way to describe force, when we're talking about a variable force is the integral of f dx from x initial position to x final position. So you're going to sum up all of those little f dx's, and that's how you handle a variable force. But this situation was only looking in one direction. What if instead we were looking at a varying force in 2 dimensions? So you've got fxi, fyj, fck, and all those are varying. What we do is, instead of thinking about f dx, we're going to think about f dot dr, where dr is the change in x plus the change in y plus the change in z position. Well, this isn't too hard for us to deal with, because what we can do is think about, our work is f dot dr. So it's our force times a little bit of distance. And that little bit of distance, dr, is in the x and y and z direction. Well, using dot product, we see very quickly that this is just fx dx plus fy dy plus fz dz, and that whole thing needs to be integrated so we can find the total work. And we're going from x initial to x final, y initial to y final, z initial to z final. So in 3 dimensions with a variable force, what we're going to have is 3 integrations for the x, y, and z components. That's it for now.